Hello, everyone. Welcome back. So today we're going to be talking about proof by cases. I'm going to talk about the questions that you asked on Katie. I'll open it up for you to ask any questions that you want about various proof by cases related things. I'll do some more examples for you where I give you a bit of time to work on it, and then we talk about it together in hopes of giving you a little bit of practice and a little bit of insight into at least how I think about these things. Also, I've posted your test grades together with some feedback. I tried to write each of you a pretty detailed statement of where I think you are in the class in terms of like, is your writing good, or do you need to work a little bit on that, or is there a particular area where you're missing a lot of things? So I tried to offer you a pretty holistic set, or a pretty holistic picture of where you are. So please go on, Katie, and read the comments and read through your exam. Note for many of you, I wrote comments even on things that I gave you full credit on, so something like, well, really, this isn't quite the right word. So it's worth going back and reading those things. All right. Uh, Before I jump too deep into talking about proof by cases, I did want to give you a small tech tip for today. And so this is something that I know has bothered some of you, is that, like, if you want to do something like this Z, it gets annoying that every time you type this, you have to type this. And that looks a little bit, it's kind of a lot. If you put in your header, there is this thing called new command. And what new command lets you do is it lets you define your own command. So you might want to define the command \ZZ and then something like this. And so if you put this in your header, then what this tells LaTeX is, hey, every time I write \ZZ, I want you to just replace it with that. And so if you find yourself using something a lot, you can throw these things in the header and then use it as part of your own template. So you can make it so that \ZZ is always this Z, and likewise \RR or \QQ or whatever other symbols that you want. And so if you want to do this at the level of sophistication that I am at, which is to say at a lower level of technical sophistication, you can copy paste or just duplicate a file and open it as a means of transferring your header information from one file to another. But if you want to be more if you want to be more fancy about it, what you can do is you can make a header file of your own that you attach at the beginning of each thing, and Overleaf will make that fairly transparent for you. And the more you do this, the more adventurous you are. You can even make new commands that have parameters in them, so you can make new commands that will write more complicated things than just a particular letter. Again, some of you will really enjoy digging into this, and some of you will immediately forget that I ever mentioned any of this. For me personally, I usually just take people's code for new commands off of the internet if I'm looking for a command to do something, but you can certainly write your own. LaTeX is very, very powerful, so you can do all manner of things of that sort. Okay. That was a long-winded introduction. But let's hop back into your questions. So someone asks if you can use proof by cases if the question contains the phrase "at least one of." And the answer is that you can use proof by cases in something that asks you to prove something with an at least one of phrase as long as this is in the hypothesis. So prove that at least one, or something like, prove that if at least one of x, y, and z is even, then x, y, z is even. That is a perfectly appropriate time to use proof by cases. Someone asked what's always the key question, which is, how do you know when to use proof by cases? And the answer for me, at least, is proof by cases is always the last resort. So I'm never leaping to have the option to use proof by cases. It's very rarely going to be the thing I start with, unless the question is phrased in such a way that it beats me over the head with it. Like if the question is framed in terms of if x is blah or y is blah, then do this, well, then you're sort of forced into proof by cases if the contrapositive doesn't work. But in general, I want to save proof by cases until I'm stuck, because proof by cases proofs tend to be longer than other proofs. Which isn't the same as saying they're harder. They're usually just messy and long. But the overall idea, and I tried to emphasize this in the video, of proof by cases is not something new. We've been doing this plenty throughout proofs up until now, where we said something like, okay, well, if I know one of these two things is true, I'll just sort of look at the universe where each one is true. We've just sort of formalized how to write it down. Okay. Someone else also asked about, like, is there an easy way to know if something is a proof by cases or a proof by contrapositive or whatever? I've tried to give you a lot of hints on when something is a proof by contrapositive. I think proof by contrapositive is something that stands out at least when it's worth trying. But I would always start with direct proof unless I see some structure that basically lets me know in advance that direct proof isn't going to work. And then look at the contrapositive, but particularly if there's something like an or in the conclusion, things with ors in the conclusion, things with excessive use of the word not. These are the sorts of things where proof by contrapositive will show up more. But again, it's ultimately an intuition thing where you'll do enough examples that you'll start to see some patterns, although you'll still find that you'll get surprised by these things. It's probably also worth noting, probably the most common way that you'll come across something requiring a proof by cases is you'll be trying to write down a direct proof, and you'll realize that you don't know a piece of information that you need to know. And so I'll do an example of this later, but you might well come across something where you're like, well, I really want to know if this x is even or odd, but I don't have any way of knowing that. And so what you're doing in proof by cases is you're basically saying, well, okay, what if I did know the answer to this question, and the answer to this question was that x was odd, then what would the world look like? And then as long as you can also answer it in the case when x is even, then you're in good shape, and so then you can do it both ways. So it's basically a way of fabricating information that you don't have, is one way to think about it. And so anytime you find yourself in this sort of like wishful thinking point of view where you're like, this would look a lot like a kind of proof we've done before, if only I knew fill in the blank, then you might consider making that a case and then trying to flesh out around that what the actual proof would look like and what the other cases would look like. Now, the further you go, the more complicated the proofs get, and the more it might turn out that if you can only do it in one case, maybe that's telling you you're missing some fundamental piece of something that you're not doing. At the moment, our proofs are usually pretty short, but they're getting longer and more complicated, and in other classes they will get longer and more complicated, and so then you might have to do a lot of thinking through different logic and try a bunch of different things before you find the exact combination that works. Someone asks, if two cases are similar, but not all of them, is it appropriate to use without loss of generality? And the answer is yes. So here's how I would write that up. So let's say that what I know is x is odd or y is odd. And I need to break this into cases. And suppose breaking this into cases where I do x is odd or y is odd, suppose that turns out not to be enough. Okay. Then I could break this into two cases, as case one is x is odd, x or y is odd. And then case two would be x and y are both odd. And as long as the problem is symmetric in x and y, then I'm perfectly okay to say here, without loss of generality, suppose x is odd. And so on. So if I'm in a case, if I'm in a proof where there's cases and two of the cases are identical and a third isn't, you can really sort of merge those two that are identical into one case and then put your without loss of generality there. Someone asks, how do you know how many cases there's going to be? And so there are a couple of times in the video where I ask you to pause the video and think about how many cases you're going to need. And that's because this is sort of an intuitive thing where you have to sort of think through and imagine what it's going to look like. And it's worth noting, this isn't a well-defined number. It might be that I write a proof with 2 cases and you write the proof with 4 cases. Or I write the proof with 3 and you write it with 5, or whatever. So you might end up using more cases than you technically need. I did an example in the video where I think the quote-unquote easy way to do it was 4 cases, but then at the end I showed you that actually if you thought about it right, you could do it in 2 cases. So that's worth considering, but you're never going to know until you've covered all the possibilities. So if you start with saying, okay, well, I can prove this if x is even, then you're in good shape if you then show it when x is odd. But you might end up with something like, okay, well, I can prove it when x is even. By the way, these are just outlines of hypothetical proofs. Just to be clear, I'm not giving you an actual question. I'm just showing you sort of hypothetical outlines. And so maybe you can prove it when x is even, but then you can't prove it when x is odd. And so then maybe you figure out, but I could prove it if x was 4k plus 1. And so then the question is, okay, well, if these are my first 2 cases, what am I missing? What do I need to figure out? I need at least one more case. And so what's the third case here that would finish this off? Yep. exactly. X is 4k plus 3, right? And so this is just the division algorithm here, where when you divide by 4, everything looks like 4k, 4k plus 1, 4k plus 2, or 4k plus 3. And even actually handled both of these buckets. And then these each got sort of put into their own case. But the division algorithm explicitly tells us that these are all possible numbers. They all fall in these buckets. It's worth noting, by the way, these are called the mod 4 buckets. So when you hear people talking about something mod 4, a number mod 4 is just telling you the remainder here. So this is 0 mod 4, 1 mod 4, 2 mod 4, 3 mod 4. Do you need to cite the division algorithm when laying out cases like this? I probably would, but I don't know that I would complain if you didn't. Of course, be sure you do it correctly. In general, a big part of writing proofs and getting responses to proofs is that you can get away with sort of claiming a lot as long as you're always right. But as soon as you falsely claim something, then that causes whoever's reading your proofs to read them more closely. And so if you falsely claim something in one particular proof, and then you make similar claims that were correct in other proofs, then it calls into question whether you really understood the things or not. And so I think there's a lot of levels of detail and exposition that are acceptable in proofs, though you definitely want to make sure that you're writing at sort of an even level of detail. That is, you're always writing more or writing less. Sort of like one of the telltale signs that someone doesn't understand what's going on in a proof is where they skip over a bunch of detail and then go into in bloody detail some algebra calculation or something. And so you want to try and make your writing style even. By even, I just mean at about the same level of detail throughout. And as long as you do that, there's a lot of acceptable things. So I wouldn't complain if you just said, these are the 3 cases. But I think it's probably worth a note if you have some unusual combination of cases like these. Next, someone asked if you could use proof by cases on number 5 on the test, which was this x squared plus xy plus y squared question. Yes, you certainly need to, in some sense, use something like proof by cases. You need to sort of identify that, okay, what I'm given is that x is odd or y is odd, and you have to figure out how to work with that. And so you have to sort of work through the possibilities. This is a case where I don't think it's sort of like not a new kind of proof by cases. We've been breaking into the like, okay, what happens when x is even? What happens when x is odd? A lot through the course. But yes, you certainly could write it in that parlance now if you want. Someone asks if claims and lemmas are the same thing. And the answer is basically. Usually if you're writing a longer text, so like imagine you're writing a senior paper or something, if you make a lemma, usually you'll number it. So this will be something like lemma 1.7. And so then you can refer to it later in the paper, whereas if you make a claim, usually you will not number it so that you will not be able to refer back to it later in the paper. Also, usually in typeset formal writing, usually you put the lemmas out of the proof. I, in the video, sort of showed you putting it in the proof, which is not uncommon, but more often you'll see lemmas sort of floating outside of a proof. But they're both doing exactly the same thing for you, which is letting you pull a piece of the proof into its own little universe where you're dealing with something smaller, so you're not having to deal with as much of the whole problem. So basically, they're the same thing. That is a long way of answering yes, they're basically the same thing, but with slight nuance. Someone asks if you need to justify why the cases cover all possibilities, which is similar to May's question in the chat. Uh, Only if all possibilities is weird in some sense. Like, if it's not obvious that you're covering all the possibilities, then you should make a note. But most of the time, it's going to be pretty clear. Like, if your cases are that something is even and something is odd, I don't think you really need to note that, oh, by the division algorithm, every integer is even or odd, so we can break into these cases. But if it's not something, if it's something that you would pause when you were reading someone else's proof and be like, wait, why is this all of the cases? Then you should definitely include it. Someone asks, in the making your own cases video, where on earth did you get the x squared from? Which was a kind of mysterious question when I read it, so then I went and looked at the video, and there's now a comment at the top of the video, and for reasons that are beyond me, in the video I write on the paper, prove that for every x in z, there exists a k such that x equals 4k plus 1 or x equals 4k. But I don't mean x, because that would not be true. There are 4 kinds. I mean x squared. And if you see it in the context of everything, I've just proven that statement, that x squared is always in one of these two buckets. And then I'm proving it again in a different way. And so you can probably guess that that's what I mean. But for whatever reason, I wrote completely the wrong thing on the sheet of paper. So bear with me on that. Okay. And next up, someone asks if lemmas are something you have to use. And the answer is no, you're probably not going to find yourself using them too often on something like the homework in this class, or even probably the homework in most undergrad classes. They're something you'll almost certainly want to use in your senior paper, if you do your senior paper in math and that kind of thing. And there's something that you're going to see a lot, both in professor's lecture and in textbooks when you're reading them, because they are a very big part of the parlance of math. And so sort of in this course, we're sort of simultaneously teaching you to produce proofs, but also to read and appreciate proofs. And there's a big difference in the kind of proofs that you're expected to produce versus the kind of proofs that you're expected to appreciate. And so in a music class, you might listen to Beethoven, but that doesn't mean that the professor is going to expect you to make Beethoven-style music. In the same way, probably you're not going to use lemmas a lot, although there are definitely going to be times where it'll make your proof a lot cleaner if you realize that you could sort of pull out a piece of it and handle each piece separately rather than doing it all together. Annoying technical note, the plural of lemma is technically lemmata. But some people will say lemmas anyway, and either way is fine. But you'll see lemmata now and then, which is just the Latin plural of lemma. Okay. So before we go on and get to my examples... Oh, that's right. There's one question from the homework. Someone wanted me to talk about 32 and 34 from the homework. Let me pull those up and say some words about those. Are there any other homework questions? You can throw numbers in the chat that people want me to say a couple words about. As far as 32 goes, I'm going to do an example that's a lot like 32. someone asks if you can just say that 4k and 4k plus 2 are even, or if you need a lemma. And so now that we're past the first test, I will not complain if you just tell me 4k and 4k plus 2 are even. Okay, and then someone wants me to talk a little bit about non-differential sets. So that is number 35. Okay. 32, I'm going to do an example that's almost exactly like 32, so I'm going to pause on talking about that one for now. For 34 says, prove that if A and B are subsets of the universal set R, so A and B are subsets of R, which I've defined to be my universe for this question. And so it is prove that A union B complement equals R if and only if A is a subset of, if and only if B is a subset of A. Okay, so the question here is really about how to set this up. So there's a few pieces to the structure here. So first of all, there's this phrase if and only if, which tells you that in your proof outline, you're really going to need sort of two sections. So you're going to need a forward section and a backward section. And so the forward section here is going to be to prove that if, so this is the thing you want to show, if A union B complement equals R, then B is a subset of A. And on the backwards direction, you want to show the opposite. That is, if B is a subset of A, then A union B complement is equal to R. Okay. So if and only if proofs are always going to have this structure where you're going to, and just to be clear, I'm not writing out the proofs of the pieces. You're always going to have this structure where you're going to prove each piece. And you should definitely state the direction you're proving as you prove it. So something like just writing the if-then statement and then the if-then statement the other way or whatever. Okay. And then once you break it into those pieces, then you can use whatever techniques you want on each piece separately. So for example, in this case, I would definitely use proof by contrapositive on the first one. So I would say, after saying, okay, this is the if-then statement I want, then I would say, okay, we prove the contrapositive, and then write the contrapositive of this piece. And here I would use direct proof and write it out that way. And then, of course, note here you're showing that two sets are equal, which means that you're going to also have a mutual inclusion piece in your proof, although it's not so difficult to see that A union B complement is a subset of R. It's the other direction that sort of ends up being interesting. Okay. I really encourage you, by the way, and this was a common note on the test, to use these sort of clear section markers just to break your proof into pieces. And really, this is just a way of telling you, break your proof into coherent paragraphs rather than having a big wall of text with no space in it, just because it makes things easier. And so when you go to sort of start a new idea or a new piece, you should definitely start a new paragraph, and then you can head that off with the appropriate symbol if you like. Okay, so then we have a question about a non-differential set. So just an example of a non-differential set. So what does non-differential mean? So the definition is, this is, by the way, this is number 35. A subset A of Z. Z or Z plus? Z. Non-differential. If for all x and y in A, we have x minus y is not an element of A. Okay, so here is a non-differential set. And so what we're claiming here is no matter which pair of x and y I choose, so I can make a table of all the possible x's and y's, 1, 3, 8, 1, 3, 8, and then write x minus y in the box. So 1 minus 1 is 0, 1 minus 3 is minus 2, 1 minus 8 is minus 7, that would be 2, that would be 0, that would be minus 5, again, 7, 5, 0. And so I've now shown you every possible pair of x and y. If I subtract them, I end up with something not in the set. Is that a sufficiently complex example to make sure you understand what the definition is saying? Whenever you're working through these questions, it's worth having an example in mind where you sort of follow through that example in your proof if you're trying to prove something. And when you're looking for those kinds of examples, you're looking for fairly generic examples. And what I mean by generic is you want something that is complicated enough that you think it probably captures all of the nuance of the question, or at least as much of the nuance of the question as possible, without being sort of overly complicated. And so, for example, when someone says, okay, what's an example of a non-differential set? You could certainly say, oh, the empty set is non-differential, but the empty set is probably not a useful example of a non-differential set for understanding and developing an intuition for what's going on in the various problems. Okay, are there any other questions before I jump into my questions about proof by cases? Okay, so as before, I'm going to write up an example, and then I'll give you a few minutes to think about it, and then I'll go through it with you. Sorry. I'll give you to 11:40 to think about this. Okay, welcome back. So we want to try and prove this. And so note this is an if and only if question. So we are going to have to formulate both directions of that. And so there'll be a forward direction and a backward direction. Now, most of the time, when you're doing an if and only if proof, one of the directions will be easier than the other. And so often it will be sort of a game to figure out, okay, which is the easy direction and which is the hard direction. Although, of course, it doesn't matter if you get it right or not. But we can look at this one. Okay, so we have a forwards. I don't know why I put a colon in the thing. You probably don't need a colon if you have a parenthesis. Okay, so for the forward direction, what are we proving? If x squared is greater than x, then 0 is less than x is less than 1. And then for the backwards direction, we're going to be proving if 0 is less than x is less than 1, then x squared is less than x. So let's do the backwards direction first. So let's do this piece first. Okay, so we're going to suppose that 0 is less than x is less than 1. Okay. And it's important to remember this is just shorthand as a way to say 0 is less than x and x is less than 1. Okay. And so now, what does the fact that 0 is less than x tell me? Well, it tells me that x is positive. And so since x is positive, then that tells me I'm allowed to multiply inequalities by x without changing them. And so when I do multiply this by x, I get x squared is less than x. And that's the thing I wanted. Okay. Questions about that direction? Again, please remember if you want to multiply both sides of an inequality by something, then what you have to do is you have to look at whether the thing is positive or negative, because if you multiply both sides by a negative number, remember that flips the inequality sign. So if you've not thought about that in a while because you haven't solved inequalities since Algebra 1 or something, be sure you remember that. Okay, so now let's go over the proof in the forward direction. Oh, sorry. Where do you include the back arrow in the proof? So, in my mind, this is part of the proof. I would write it this way, and so I'm including here maybe the proof I would put up at the top, but I would group together this statement with the back arrow and the proof of it. It's an aesthetic choice whether you want to put the subheading proof in your proof multiple times or not. So if you want to say, okay, I'm proving the forward direction and put the word proof there, or PF for proof, then you could do that, or you could only have it at the beginning. Either way is okay. Okay. So even though we didn't need to use cases in the previous problem, we alluded to the thing we're going to need cases for, which is that we're dealing with an inequality here. And of course, what I really want to do is divide this inequality by x. Because if I divide this inequality by x, I'll get x is less than 1, and that looks suspiciously like the thing I'm trying to prove. Okay. But because of the way signs work, I need to actually pay close attention to whether x is bigger than 0, less than 0, or equal to 0. Okay. And so I'm going to break into cases here based on the sign of x. So let's look at x equals 0 first. So if x is 0, then x squared is less than x is false, right? So the implication is true. Okay. Here we have to think again about this detail we don't really like to think about the way we defined implications at the beginning, where an implication's automatically true if the hypothesis part is false, right? And so if x is 0, 0 squared is not less than 0, so I don't even have to think about this piece. Okay, case 2 is x is less than 0. So then x squared is positive, but x is less than or equal to 0. So what that means is that x is less than or equal to 0 is less than or equal to x squared. So in fact, actually, it's strictly less, so I can actually get rid of these or equal to bits. So x is less than x squared. So what does that mean? That means x squared is not less than x. And so again, in this case, we actually conclude the implication's true because the hypothesis is false. Okay, so then our final case here is that x is greater than 0. Okay, and so since x is greater than 0, 1 over x is positive. And so we can multiply this inequality by 1 over x, which ends up giving us x is less than 1. Okay, so here I'm trying to say that if x squared over x, or sorry, if x squared is less than x, then 0 is less than x is less than 1. Okay. The fact that 0 is less than x is part of this case. So really here, what we've exactly shown is thus 0 is less than x is less than 1. And then we're done with this direction. Okay. Questions about that? Could you do a proof by contrapositive for the second part? So the second part, if you wrote down the contrapositive, this, by the way, is me saying, I don't know, maybe. If I wrote down the contrapositive of this, it would be if x is greater than or equal to 1 or x is less than or equal to 0, then x squared is greater than or equal to x. That's the contrapositive. And that looks true, and it also looks like something that we could naturally prove with cases. So if x is greater than or equal to 1, then x is positive, so I can multiply this by x, which gives me x squared is greater than or equal to x. Or if x is less than or equal to 0, well, then what does that tell me? That tells me that x squared is positive, but x is negative, so that gives me this piece. So yeah, proof by contrapositive works and is maybe a line shorter than my proof. Any other questions? I mean, one of the best parts for me about teaching proof-based courses is that almost every time I get some novel proof of something that I had not really at all intended. And so it's neat that so many of these things can be done in different ways depending on how your brain works and these sorts of things. Okay, so this question really has two parts. So I want to walk you through what the two parts are before I give you some time to work on it and think about it. So the first part is you need to prove to me that this thing's always an integer. And there's something to prove there because of this divided by 2. Right? 7 halves, for example, is not an integer. And so I do have to worry that maybe there's some n where it happens that this thing is not actually an integer. Maybe it's a rational number with denominator 2. Okay, so that's part 1, is to prove that. Okay, but, spoiler, it's true. And so then I want to know, okay, so once you have proven that it's true, when is this integer even? Okay. And so in order to figure out when it's even, you're going to have to collect enough data about this number in order to make an educated guess as to what integers n have the property that this number is even. And then you'll fill in that educated guess here, and then you'll prove this if and only if statement. So that's the goal. And I should note to a question from earlier about question 32 on the homework, this is very similar to question 32, so this should be good preparation for that. Okay. But I'm going to give you a good chunk of time to think about this because I'm actually asking you to do a bunch of things. So I will give you until, let's say, 12:10 to think about this, and then we'll reconvene and we will talk about it. But in particular, this is a great time if you want to go grab coffee or whatever to go do that. And then we'll talk again in a little bit about how to do this question. Alrighty, welcome back. So, there are cases all over this, but let's start with let's start with the first part. So let's prove this thing is an integer. Okay, so here's a perfect example of where we kind of know what we're really being asked to show. Namely, this is really asking us to show what about the numerator here? Oh, it's divisible by 2. Do we have another name for that? I mean, divisible by 2 is fine, but I think there's another name that we like too. Right, so we really want to show that n times 3n minus 1 is even. Okay, so let's try and now show that. So if n is in z plus, n times 3n minus 1 is even. Okay. Note here, I'm really viewing this as scratch work. That's just why I have all of these want-to-shows floating around, just to sort of translate the problem in as many ways until something sort of sticks. But at this point, now it's pretty clear, I think, what I should do, namely, which is to break into cases based on whether n itself is even or odd. Okay, so let's prove this. So suppose n is in z plus. And so first case. Is that n is even. Okay, in this case, there exists k and z such that n equals 2k. So n times 3n minus 1 is 2k times 3 times 2k minus 1. And so if m is, we'll say, k times 6k minus 1, then we can see that n times 3n minus 1 is 2m, and so it is even. Okay, or instead of it, I should probably say n times 3n minus 1. Okay, and then the other case is that n is odd. So then, likewise, there exists k and z such that n is 2k plus 1. So n times 3n minus 1 is 2k plus 1 times 3 times 2k plus 1 minus 1. Which is 2k plus 1 times, and then that's going to be 6k plus 2. And so that is going to be 2 times 2k plus 1 times 3k plus 1. And so if I let m be that second mess, then n times 3n minus 1 is 2m. So n times 3n minus 1 is even. Okay. So in both instances, this thing is even, which means that you can divide it by 2. So this thing is an integer. Okay. Now, you might ask at this point, why did this use proof by cases? So you can probably understand why you had to use proof by cases to do it, but you can ask the sort of deeper philosophical question, what is it about this problem that made you have to split into odd and even cases, even though there's not actually any reference to odd or evenness in the problem? Okay. And the answer to that, if you sort of dig through this, is that if you look at this thing that I want to show it's even, it's a product of two things. Okay. And remember, we've shown before that x times y is even if x is even or y is even. Okay. And so this product of n and 3n minus 1 is going to be even as long as n is even or 3n minus 1 is even. Well, if n is even, well, this is kind of a silly statement. If n is even, then n is even. Yeah. If n is odd, well, then n is odd, but then 3n minus 1 is even. Yeah. And so the reason why this ends up having cases is that which half of this product is actually even depends on whether n itself is even or odd. Okay. So even though at first it looks very artificial and weird, if you actually dig into it and look into what we actually proved, you can actually see why it turns out to be the case that you really need to think about this in terms of whether n is even or odd. Okay, next up, we need to collect some data about this. So let's calculate enough of these to have a guess about what the answer is. Okay, so 1 here, if I put it in, I get minus 1, right? Sorry, I don't get minus 1. I can't multiply. I get 1. How about that? 2, I get 5. 3, I get 3 times 8 over 2, which is 3 times 4, which is 12. Here I get 22. When I put in 5, I get 5 times 7, so that's 35. When I plug in 6, I get 3 times 17, so that's 51. When I plug in 7, I get, let's see, 20, so that's 10, so that's 70. When I plug in 8, I get 4 times 23, so that is 92. And when I plug in 9, I get 26, so 13 times, I get 13 times 9, which is 117. Does anyone disagree with any of my numbers here? I don't promise that I did all of these correctly. I don't see anyone disagreeing yet. So I'm going to circle the ones where it turned out to be even, because that's what we were asking about. So those two, these two. All right, looking at this data, do you have a guess as to what the pattern is? Namely, do we have a guess on what goes in the blank in the original question that I gave you? Right, so it's if n is a multiple of 4 or 3 more than a multiple of 4. And that's exactly what we have to prove. Okay, so let's walk through proving this. Okay, so this is going to be an if and only if proof, which means we're going to have to do this in both directions. So I am first in the proof here going to write down the backwards direction. So here I want to show that if n equals 4k or n equals 4k plus 3 for some k and z, then n times 3n minus 1 over 2 is even. Okay, so this definitely primes us to think about cases because of this or here, right? So this or tells me there's sort of two universes I have to think about. I have to think about the 4k universe and the 4k plus 3 universe. Okay. And so I'll do that. Okay, so then when I look at this thing, it is 4k. And basically, as soon as I write down the 4k, if I'm paying attention, I know what's going to happen. 12k minus 1 over 2, which is 2k times 12k minus 1. So if m is k times 12k minus 1, then as it happens, then this thing is 2m. So it's even. Okay. Check mark 1. Okay. Case 2. So case 2 here is that n is 4k plus 3. So then this thing, n times 3n minus 1 over 2. This is now 4k plus 3 times, and then this is going to be 3 times 4k plus 3 minus 1 over 2. And I'm going to have to do a little bit of algebra here. So this is 4k plus 3 times 12k plus 8. Okay. And so I can factor a 4 out of this, and so this will become 2 times 4k plus 3 times, and then 3k plus 2. And so if m is this whole thing, then this is 2m, and so we're done. Okay, so that finishes one of the directions, right? That finishes the backwards pointing direction. And so, just to take a macro look at this for a second, I think all the steps in this proof are basically things that we have been doing since we started talking about proofs almost. But the macro structure of this proof is fairly complicated because I have to deal with 2 different directions, and then I have to deal with cases in both directions, and I have to throw in a contrapositive there, and all these sorts of things. So this is really an exercise in keeping track of the structure of a slightly more complicated proof. Okay, but let's structure-wise, let's at least finish setting this up. So what's the other direction going to look like? The other direction, I'm going to need to be proving that if n times 3n minus 1 over 2 is even, then, and so now I have, well, then, sorry, let's finish writing this before I say more. N equals 4k, or n equals 4k plus 3. Okay. What do we have to do to prove this statement? Contrapositive, right? And so this is the very typical example of what some ugly thing that you have to use the contrapositive one is going to look like, because the hypothesis is because the hypothesis here is about some complicated formula, and then the conclusion is something simple about just n. Okay. And it also has an or in it. So we're going to need to prove the contrapositive. And we actually have to be a little careful when we go to write down the contrapositive, because if we sort of mindlessly write down the contrapositive, when we negate this, we're going to say, for all k and z, n is not 4k, and n is not 4k plus 3. And while everything here is not incorrect, this is a pretty useless hypothesis. Is there a better way I can write this same piece in blue? Right, exactly. Everyone is right. So, by the division algorithm, remember everything is in one of these four buckets. You can ignore everything but the buckets. And so not being in the 4K bucket or the 4K plus 3 bucket means that you are in the 4K plus 1 bucket or the 4K plus 2 bucket. Okay. And so what I actually want to write here for the contrapositive is if there exists a K such that n is 4K plus 1 or n is 4K plus 2, then n times 3n minus 1 over 2 is odd. Okay, so this is our contrapositive, stated in a way that is helpful. Okay. And so now, to finish the proof, we suppose that there is such a K, and then we do the two cases that we did before. Okay, and I'm not going to repeat the same proofs. I think you could fill in the details from here, but we'd have these two things. And then finally, at long last, we would be done, because we would have proven the if and only if direction, one by direct proof and one by contrapositive. And then in each of those proofs, we would have needed to sort of resolve things into cases. Now, on the one hand, this is messy and a little bit complicated. But if you follow our sort of ways of heading things, this is very easy to read and check. Because we'll have, again, sort of a forward arrow, a backward arrow. We'll state the contrapositive for the reader. We'll label our cases off separately. So it should not be too hard to follow once this is all teched up in a nice way. And what we did here is actually pretty powerful, if you look back at it, which is to say, we looked at this minuscule amount of data. We just looked at 9 points of data, and we guessed a pattern from 9 points of data. Now, certainly from reading this Law of Small Numbers paper, you should definitely not believe any pattern that you see from 9 points of data. But once we guessed what the pattern was, then we were able to write it down as a conjecture, and then we were able to prove it. And so now actually, basically just through the combination of 9 points of data and our proof skills, we now actually know for a fact that exactly the even ones are every third and fourth out of 4 of these things. Okay. So That's really how math progress works. Someone notices a pattern, and then someone proves it. And they might be the same person or they might not be the same person. But together, these have sort of given us the true answer to this original question that we wondered. Okay, any questions about that question? Okay, let me give you one more to look at. J. That is equal to, and I want 2 to the I plus 5j. Okay, so I think this was my proof by cases question last test that I gave on this topic. So this is a good practice question. I'll give you, we'll say, 7 minutes to look over this, think about it, try and figure out what the cases are, try and figure out what the structure of the proof looks like, try and make sure you're parsing out exactly what you need to show with this there exists statement. Don't get tricked into thinking you can show me just one example. And then we'll reconvene and after, we'll say 7 minutes, and we'll talk about it, and then we'll wrap up for today with questions and office hours for anyone who has more they want to talk about. Alrighty, let's talk about this question. So, first of all, what are my cases going to be here? Right, they're going to be based on the buckets mod 5. So, I'm going to say here, so if n is an integer and not a multiple of 5, so then what does that tell me? That tells me then there exists a k in z such that, and then n is one of these 4 things. Sorry, 5k plus 1, 5k plus 2, okay. And so here I'm spelling this out, and I guess this is sort of an answer to some questions earlier about, do you have to explicitly cite the division algorithm? Do you have to explicitly say what your cases are going to be before you do them? Here, I guess I'm sort of halfway doing both of those things. I'm listing what all of the possibilities are so that it's not too surprising when we then write out these as cases. Okay. So I've got this thing here. Uh, Actually, I want to make one more note here, which is that because my n is positive, actually, there's not just a k and z that makes this true. There's actually a k that is at least as big as 0 that makes this true. And that will make clearing up the fact that I and j here are going to be greater than or equal to 0 a little bit easier. Okay. So now when n is 5k plus 1, I need to explain what I'm going to choose I and j to be. And those I and j are allowed to depend on k. But again, please note I cannot just say, well, 11 is whatever 11 is, and so I'm done, because 11 is a particular number, and I need to show this for all n. So this is another one of those for every there exist kind of statements where I need to give an example for every instance of the variable n. Okay. So here I want to choose I and j. What do I want to choose I and j to be in this instance? I want to choose I to be 0 and j to be k. I absolutely agree. So if I choose I to be 0 and j to be k, well, then what do I get up here? I get 2 to the 0, which is 1, plus 5k. That's the same thing as n. Okay. So here I've given just one example, but I've given just one example for every case. Sorry, case is a poor choice of word to use because we're in cases. I mean, I've given here one example for every possible k. And so this is a good picture of what it looks like when we're proving a for every there exists kind of statement. Okay, so then let's go through the others. Case 2 is n is 5k plus 2. Okay. Now I think we'll agree that we can choose I equal to 1 and j equal to k. Because then I will get 2 to the first power plus 5k, which is 5k plus 2, which is exactly the thing I want. Things get more exciting in the other two cases. Okay, so here it ultimately ends up being the case that I want to choose I equal 3 and j equals k minus 1. Okay, and now this probably warrants explanation. And this is because then 2 to the I plus 5j ends up being 2 cubed plus 5 times k minus 1, which is 8 plus 5k minus 3 minus 5. 5 times 1 is 5. Apparently I messed that up. And that is 5k plus 3, which is the thing that I want for that case. Okay. Did people find this for case 3? You have to sort of look around. There's not some obvious way to go about finding this other than sort of trial and error to figure out, okay, I've got to get something that's going to take care of the 5k plus 3 bucket. And so you look around at your powers of 2, and, well, the first power of 2 that happens to be in the 5k plus 3 bucket is the third power of 2, 8. Okay, which is why this ends up working out like this. And then the last case here I really don't think you need more than this. I mean, it wouldn't go astray if you said then 2 to the I plus 5j is 5k plus 1, but I would be perfectly happy with this as my entire proof for this case. Likewise, for this one, I think we can really say choose I is 2 and j is k and be done. Okay, so that concludes that proof. So now I am done with my examples for the day. However, if you want to hang around and ask questions, now is sort of the office hours time. So if you've had a chance to look at your test and you want to talk about any particular question from your test, or have me go over how to do it or whatever, I'm happy to do that. Or if you prefer, I have office hours tomorrow. That might give you more time to look over your test, and you're welcome to stop by then at 11. Uh, Remember, the homework is still sort of due at the times when it says. I was able to give a little bit more uh, flexibility on the schedule this time, because remember, the test is not till a week from today. So I staggered the homework a little bit more, so it should be a little more humane than the homework due date schedule for last week was. So that is the agenda. But anyway, if I don't see you today, or sorry, if I don't see you tomorrow in office hours, I'll see you Wednesday, and I hope you are having a good week. Can I talk about how to start number 31 on the homework? Yes. Uh, so, number 31 on the homework is asking you to show that it's possible to write every integer as a sum of three distinct integers. So, I think a good way to start is to do a whole bunch of examples and try and find examples that you can write formulas for. And I think for me, the natural way to handle this ultimately ends up involving the mod 3 buckets, but there are lots of ways to do this, depending on exactly what style it is. But this is one where it's really not clear at first exactly what your formula is supposed to look like, so you really need to look at a lot of cases and then eventually sort of guess what's going to end up working. Just remember to make super sure that whatever formulas you write down, that it's very clear that the three things you write are actually distinct. Yes, let's talk about 8C from the test. Sorry, that's the wrong test. One moment, let me pull up the right test. Oops. Okay, so let's just copy down the definition of stranded real quick. So a subset of Z is called stranded if there is an element that has no adjacent element. X in Z, sorry, X in A, such that X minus 1 is not in A and X plus 1 is not in A. Okay, I think I've now copied the definition correctly. And so 8C says prove or disprove that if A and B are stranded subsets of Z, and they intersect non-trivially, then A intersect B is stranded. Now, it's probably not obvious when you first look at this question whether the answer here is actually that yes, it's true, or no, it's false. And you might even start to try and write down a proof for it. But hopefully, your proof will fail because it's not actually true. And so, what can happen, roughly speaking, is that this X that happens to satisfy this condition for A is not an A intersect B, and the X that happens to satisfy the condition for B isn't an A intersect B. And so I can take something like A is 1, 2, 4, and B is 1, 2, 5. These are both stranded, but their intersection isn't. Okay, so this is a counterexample. And so I wrote notes to several of you on your exams to the effect of that you have very good intuition, but that it can get you in trouble. And so what happened was a few people wrote down a proof of this that went something like, okay, well, because A is stranded, there's some X that works for it, and the same is true for B, and the intersection's non-empty, so then that thing is in there, and whatever, whatever. And so there are different people whose brains work different ways. Some people's brains are very intuitive about this kind of thing, which is great, but in which case you then have to sort of use rigor as a check on yourself to make sure that you're not proving things that aren't true. So it is worth going back, even if you now believe my counterexample. If you proved this on the test, it's worth going back and looking at your proof and figuring out why your proof was wrong. And trying to get to a point, and this is a lifelong process, where you don't let yourself prove things that aren't true. On the other hand, it's very useful to let yourself think things that aren't true. You just have to make sure you're catching yourself on a proof if you convince yourself of something that's not true. And on the other hand, I should say there's plenty of people whose brains are very rigor-oriented, where they'll naturally only write down things that are true and not necessarily think of it as from an intuitive big picture point of view, and so that also has its advantages and disadvantages. Okay. But anyway, that is 8C. Briefly go over 4C, sure. Okay, so 4C. Okay, so here's our statement. It is if S is a non-empty Z plus and the minimum Okay, so that's the original statement. And so then the converse is if S is a non-empty set, subset of Z plus, and S contains no two-digit primes, then the minimum of S is greater than 100. Okay. I'll note the question also asked you to write out the contrapositive, but for purposes of 4C, which asks you of the following three things, which of them are true? So they ask you of the statement, the contrapositive, and the converse. They ask you which of these are true. The statement and the contrapositive always have the same truth value. So I only really have to answer, is the statement true, or is the contrapositive true, because the other answer will be the same. So so let's talk about the statement. So the statement itself talks about if S is a non-empty subset of the positive integers, and the minimum is greater than 100, then this thing contains no two-digit primes. Well, it definitely can't contain any two-digit primes, because if the minimum element of this thing is bigger than 100, then it can't contain any two-digit numbers at all, primes or otherwise. Right. So the statement is definitely true. And so the contrapositive is also true. The contrapositive ends up saying if S contains two-digit primes, then the minimum of S is less than or equal to 100, which is equally clearly true, I think, because if it contains a two-digit prime, then the minimum element can't possibly be bigger than that. So it can't be as big as 100. And finally, we have the converse piece. And the converse is about this statement that if we have an unempty subset that contains no two-digit primes, then the minimum of S is greater than 100. But this is false, and I can give you a counterexample. This set contains no two-digit primes, but its minimum element is 12, so not greater than 100. Questions about that? Does that make sense, by the way? Anything else I can help anyone with? All right, folks, I'm going to head off for now. Email me if you have any questions, or I have office hours tomorrow morning, so I'm happy to answer more questions then. Have a good day.